Deepak, can you hear me?
Yes, sir.
Okay, so let us start with today's session. So welcome you for week 8 live session of Power System Engineering NPTEL course. I am Gagan Meena and I am doing PhD at Electrical Engineering Department of IIT Bombay. So we'll be following this agenda. So we will today directly take the questions. Last time we were not able to do all the questions. Right? So first of all, we will slowly solve all the questions today, and then if we get some time, then maybe in between also we'll discuss some points, important points.
Yes, sir. Sir, I have one request.
Okay.
Sir, actually, I generally go to the college, so that's why I am not able to attend all the classes. So, at the starting, please revise some points, important points.
So at the beginning of session, you want the important points.
Yes, sir.
Okay, sure, we can. We will start with that then. Okay, so I will start with the overview of week 8 then. Okay, and
Yes,
then
sir. Sure.
we will discuss the questions.
Yes, sir.
Okay. So were you able to solve the questions for the last week?
Yes, sir. I was able to, and some question were wrong. Like two question get wrong, but eight question I solved.
Good. Okay. So you remember we discussed the two methods last time?
Yes, sir. Yes, sir.
Yeah.
I
So
remember.
this week's content discuss the questions on week that two methods, means method one and method two. So I will just quickly show this that assignment 8 you have to submit by March 20th, and you can find the recordings on the live on the portal. There is a link for Google Drive. There you can get all the sessions link. So week 7, sorry, this is week 8. So week 8, first of all, there were questions on these two methods. Okay, so method 1 and method 2, both we last time we discussed the questions also for both these methods. Same was carried forward in this. So do you want me to again go through these methods, or we continue with the next topic? Deepak,
Yes, sir.
do you want me to explain these methods again, or we can move
No,
ahead?
sir. No, we can go ahead this because these matter I have solved.
Yeah, yes. So half of the session this week was covered by these first 2.5 lectures were based upon questions on these two methods. Then the next important topic which was started was the voltage stability.
Yes, sir. Sir, we should discuss this point: voltage stability and frequency control.
Yes, frequency control is in the next week. So this week was on voltage stability and approximate method for voltage drop. These two topics were covered. So we will just discuss these two topics. And then in the next week, we will discuss the application of capacitor and distribution transmission network. And then that load frequency control after that week. Okay. So yes, we will start with the voltage stability. So voltage stability now it will occur in heavily stressed system. Means when the load is very high, and it can be due to several factors. Even net load can be high. It can be so it can be due to different. It depends upon the strength of the transmission system. It depends upon the load characteristics, power transfer levels. So reactive power and voltage control limits, and then characteristics of reactive compensation components. Characteristics of these devices, and then action of voltage control devices. Okay, so voltage. What happens? Voltage stability. It leads to sequence of events. Yeah, Deepak, I think you lost the connection.
Yes, sir. Sorry, sir.
No, no problem. So I was just telling that voltage stability problem occurs when the system is heavily loaded or heavily stressed. And several factors determine this voltage stability issue, such as the strength of transmission and distribution system, what is the load characteristics, its value, and then different reactive power compensation devices that we place within the system, and how these components work, such as we have on-load step changing transformers. When the voltage reduces, the taps of the transformer need to be changed to maintain the voltage. So all these things will determine the voltage stability. So what happens when there is voltage instability? Whenever there is a voltage instability, it leads to sequence of events that will lead to very low voltages. So this sequence of event is called a voltage collapse process, and finally it leads to very low unacceptable voltages limit, unacceptable voltages in the network in in significant part of the system. So we want the voltage to be maintained, right? So we want the voltage to be within its nominal range. So say 0.95 to 1.05 per unit. So we don't want the voltage to go below this. So what happens if the voltage reduces? Then what will happen? Current will increase. And if current increases, then it can damage the equipments. So we don't want the voltage to go below certain values. If the voltage goes below 0.95 or maybe even much less than that in most of the system, at most of the buses, then it is very difficult. It's not a good situation. We need to deal with it. So this is the main thing, and I will just add one page here. So this was the main theoretical background. Then When we discussed then how to know, how can we calculate this value? How can we know by if a system is given to us, a small system is given, we have all the values load and everything, then how to know that which bus is susceptible to voltage instability issue? So last time we discussed method 2 for load flow analysis, right? Method 2 for power flow analysis. So we discussed this, which was based upon the loss calculation and the equivalent circuit model. So if we have bus 1 and bus 2, so this will be equivalent load P plus JQ. So summation of power is active power plus active power losses beyond this branch. Similarly, summation of all Q plus reactive power losses beyond the branch. So equivalent model. So in this we derived the equation for voltage. So this was the voltage equation. So it was a quadratic equation in terms of V square. That's why it comes as V raised to power 4, voltage raised to power 4. Because it's a fourth order equation. So there will be 4 solution, right? So P2 R2 plus, so P2, let me write it as V2 only. V2, so this is P2 R1 plus Q2 X1 minus 0.5 V1 square into V2 square plus R1 square plus X1 square into P2 square plus Q2 square is equals to 0. So this is the equation for the voltage. Okay. Is this fine?
Yes, sir.
So now we can also write it as like this. We can rearrange the terms. We can also write it as like this: V1 square minus 2P 2 R1 minus 2Q2 X1 V square plus R1 square plus X1 square P2 square plus Q2 square. So if we write it in general form, then it will be here, it will be P into M2, and this will be P R into JJ. JJ means branch number. So if I write it, so this is JJ branch number, this is M1, this is M2. It's the sending end node and the receiving end node. So if we solve this equation and if we call this as B and this term as C, so here we can write it as V2 and I take V2 square as X. So it becomes X square minus B X plus C is equals to 0, correct? And we will get two roots. So one is plus by 2 b minus b square minus 4c by 2 is correct. But this is equals to b2 square. So we will get two values from here also. One will be root of, again root of this value with plus and minus sign. Plus and minus sign. Is this clear? Deepak, is this fine? Do you, any doubt?
Yes, sir, it is fine.
Yeah, so we'll get four equations, four solutions from here. Two negative and two positive. Correct? So these negative values we always are not possible can because voltage cannot be negative.
Yes, sir.
So we can directly discard these two values, these two solutions. Then we are left with these two solutions. One is plus b square minus 4c. One is this, and second one is under root of this. So this also half. B minus b square minus 4c. Sorry, 2 is already outside. So this is also half. Now B is this. Voltage V1 is always, voltage is always near close to, it's close to 1 per unit. If it is 1 per unit, this is this is V square is 1. And P and R are in per unit, and R is a small value, and P is also less than 1. If you multiply two quantities which are less than 1, then resultant is also much less than 1. So these values are very small. So overall this B quantity will always be positive. Correct?
Yes, sir.
So B is always positive. And this B square is also, this 4 C value is also very less, because here R square, X square values are very small. Then they are multiplied by P square. So this is power 4. So this C value is also very less in comparison to B's. Okay, so if C is less, very small, then B square minus 4C is approximately equal to B square. B square minus 4AC we can write as B square. And if we take square root, it becomes B. So B minus B, this value becomes almost close to 0. But voltage cannot be 0, right? So this is the only one unique solution that we get here. So other three solutions are not feasible, not possible. Clear? So what now from this solution, this first one, 1 by root 2 b plus b square minus 4c under root and whole under root. So this term we are calling as sensitivity index, b square minus 4ac. So the solution is feasible when b square minus 4c is greater than 0.
Okay.
Okay. So this equation, so from here this is B and this is C. So we can write this again. Substitute, if we substitute B and C, we are saying that solution is feasible when B square minus 4AC is greater than 0. So if we substitute these values of B, we get V m1 square minus 2. So let me write here in terms of, let's say, I'm writing it for branch 1 and 2. So then it will be V1 square minus 2 P2 R1 minus 2 Q2 X1 square minus 4. This was R1 square plus X1 square into P2 square plus Q2 square. So this was value of C. So if this is greater than 0, then this we are calling as sensitivity index. So if we calculate this value for all the buses, let's say if there are 4 buses, 2, 3, 4, and here it is connected to substation. If we calculate V2, V3, V4, because V1 is already known, it is 1 angle 0. So, and we calculate this SI for all the buses, SI2, SI3, sensitivity index for all the 3 buses. So the minimum of these values, these all 3 values, SI2, SI3 and SI4, the minimum value, suppose bus 4 is having the minimum value, this is minimum, then we will say that bus 4 is most susceptible to voltage instability. That instability can, this voltage, we have to track it more carefully. If this voltage goes below, because this is the most prone to voltage instability. Okay.
Sir, more elaborate this point, like how?
Because we are saying this B square minus 4C should be greater than equals to 0, right?
Yes, sir.
So if any bus is having this value less, that means it is going towards 0, correct?
Okay. Yes, sir.
So the among all the buses, the bus which is having least value of sensitivity index, so it can have voltage instability problem when the load increases. So
Okay.
we need to track it carefully. That bus we need to monitor. So it can help us to know which bus is more prone to instability, and we can do something for it. So we can know beforehand only.
Yes, sir.
So there is one problem also in the question that where we have to calculate this voltage instability index. We'll do that. So by using this index, when we can measure the level of stability of any radial distribution network, and thus we can take any kind of, we can take particular action for that. So once this was done, so this was the first topic. Then next thing we did this, which was just discussed, was approximate method for voltage drop. Suppose, let's say we have this, we have a load here. Say this is the sending end voltage Vs, this is receiving end voltage Vr, and we have a lagging load here. Okay, and it is drawing some current IR. Okay, so we can draw its phasor diagram. So it will be like this. Say we are taking reference as Vr. Vr is reference, and we are saying that this is a lagging load. That means current will be lagging by some angle. Let's say theta. The same we can draw here also. Parallel. We can draw parallel. This is IR. So this will be IR into small r. This this is r plus jx. So we want to find out Vs. So Vs is Vr sorry Vr plus, or we can write, yes, Vs is Vr plus r plus jx into IR. So this is IR into r. We are multiplying r with this, and then if we add this x, so this becomes j IR into x. Then this becomes Vs, and this becomes IR into z. So this is clear,
Yes, sir.
and this is delta. And, okay. So now this angle is theta. So this is also theta, correct? Fine.
Yes, sir.
And this is 90 degrees. So this is 90 minus theta. So this is also theta. And then this becomes 90 minus theta. Let us hold this point is A O. This is A. This is B, and this is point C. Let me use another color. This is point C. This is C dash. This is B dash, and this is point B. This is A. Okay. So what is AB here? Tell what is AB? This length AB. How can you find AB? We know this one. We know this, and we know this angle theta. Then how to calculate AB?
Sir, cos theta.
Yes. So it will be I into R into
R cos
cos
theta.
theta. See, AB is correct. So and BC? BC is same as B dash C dash. So BC is this one. So how can you find B dash C dash? We know this. I into
Yes, sir.
I into x. So I into x cos of 90 minus theta. So it becomes sin theta. I x cos of 90 minus theta. So it becomes I into x sin theta. Correct? So AB plus BC is AC. So AC is IR I into R cos theta plus I into X sin theta. And what is O? What is OA? OA is how much? OA is this one. This is VS cos delta, correct? So OC is OA plus AC. Let me add one more page here. Copy this also.
Sir, from here, what we want to find out?
We want to find the voltage drop. This is approximate method for calculating voltage drop. So we know this Vs is VR plus I into R plus J.
R1 JXS.
So now what is OA? OA is Vs cos delta and AC is this IR I into R cos theta plus X sin theta, and this is Vs cos delta. Sorry, this is equals to, did I make some mistake? OC is this. OA is, no, sorry. OA is VR, and this OA is VR. This is OC only. OC we can write in two ways. So OC is Vs cos delta is equals to OA plus AC. OA is VR. This is OA. And OC is this. And this is AC. So now if delta is very small, then cos delta is 1. So this becomes Vs is equals to VR plus I into R cos theta plus X sin theta. Clear?
Yes, sir.
So this is approximate method. So what will be voltage drop here? From this equation, can you tell? What will be voltage drop? Voltage drop.
Voltage drop is I into R cos theta plus X sin theta.
Yes. Now, can you tell at which power factor this drop will be maximum? For that, we need to do differentiation.
Differentiate as
ED with respect to theta, we need to find out. So this will be minus I into R cos is minus sin theta plus
I
Ix into
X
cos theta.
cos theta
This
equal to 0.
is- So this is how much R by X is X by R tan theta is theta is tan inverse X by R. So if PF power factor is equals to cos of tan inverse X by R, then X by R is also this impedance angle. Tan inverse X by R is impedance angle
Yes, sir.
of this line. So when these two are equal, then it will be maximum. Okay, so this is done. Yeah, so
Sir, in practice, we will use these methods or another methods.
in which one?
Sir, in practice, like practical distribution system.
For voltage drop,
Yes, sir.
yes, we use very simple methods. Even this is used. There are other methods also. They are based upon that. For that, we need to know some other things that are this. So those methods are used. It is based upon one k factor is there. Using that k factor, we can find out. So there
Okay.
is there in some advanced courses. Here we are
Yes,
only
sir.
studying very in brief,
Yes, sir. Yes, sir.
considering the load density, other things we can find out. K factor is
Sir,
the
I have one small doubt.
yes,
Like, sir, in power system, load is vary with the whole day. Like when sometimes less, sometimes increase
yes,
suddenly. So how the power system means capable to inject that amount of power varies with the load. Like we cannot store the power, right?
yes,
So sometimes a power plant has to draw less power, and sometimes they have to draw more power.
yes.
It is automatically or some manual system is
It
there.
is automatic.
Sir, how they sense the load? Like
So it's entire control system is there. So on every generator, because generator have are generator buses are PV buses. They have to inject constant power and at constant voltage.
yes, sir.
So whenever there is a change in load, they will immediately change their set points.
Immediately they will automatically
Yes,
change.
some delay is there, time lag is there because it's a mechanical system. But very small variations are taken care by inertia of generator itself because it is a rotating mass. All the
Yes,
conventional
sir.
generator, thermal or hydro are they are rotating mass where they have very
Mhm.
huge inertia. Very
Mhm.
small fluctuation in load, even inertia is able to take care. So if
Mhm.
inertia is not able to take care, then next is the generation control. So generator has a control, group control.
Okay.
So it can uh, all the generators can set themselves, distribute the change among themselves. So all these things is done automatically. Even if after that this mismatch is there, then after few time some manual interventions are there. We have some reserves, spinning reserves they are called. Other reserves are also there. So if mismatch is not met, then those generators are called. So they are informed that please generate power so that load can be matched. Or even so those who are generating more they can be asked to reduce back down. So initial because load has to frequency has to be always maintained
Yes,
within
sir.
a very
Yes.
tight band. So for that,
Yes.
initially, very quick acting control, fast controls are there automatic,
Mhm.
and the slower controls, tertiary controls, they are manual. So mostly the primary, secondary will be able to handle all the mismatch. But if they are not able to do, then manual interventions are there. But most of the time, we are able to automatic control is able to do. It is able to bring back the frequency within its normal operating region.
Mhm. Sir,
So
for a small time frequency should disturb 50 to
yeah,
like 51, 49.
it is never 50. It is always it is some 50.01, 02, 05, something 50. You'll never. It's very difficult because load is always changing. We are switching on, switching off. Something is happening. So
Yes,
every
sir.
time frequency is little bit some deviation is there, but it has to be within this range.
50.05 to 50.05.
Nine. Hmm.
Mm-hmm.
So if it goes beyond below this, then it is a problem.
Yes, sir. Sir, like whenever the real power will change, we have to change the steam input of the turbine. And
Yes,
in case of reactive power, we have to change excitation.
yes, correct. So excitation control is there, and that valve valves are also controlled. When
Okay.
demand increases or reduces, the valve setting is changed. So valve is able to control the steam input to the turbine.
Yes, sir.
So all these things are happening automatically. All these things are done by control system. Excitation control is there, automatic generation control is there. They together they are able to maintain P and V at the generator bus. Power, active power and the voltage at that bus. If they are not able to do, then there are other controls. And if that is also not able to do, there is tertiary control. Together they will try to always maintain the system within the normal operating
Change.
region.
Yes, sir. Yes, sir. So, sir, it is very huge subject, I think, power
Yes,
system.
correct. That is, it's a very big subject. It's a huge. Even stability itself is a very big subject. Control, power
Yes, sir.
system control, dynamics it is
Yes, sir.
another.
Yes, sir. I am understanding your point. Like that's why you are doing PhD, like MTech, PhD.
Yes, each area, even power system planning is another. Protection is another area. So each area is itself a very big subject.
Hmm.
Power system analysis,
Yes, sir.
all these things we can read. There are courses on each of these topics. Power system
Uh-huh.
stability is another course. Power system planning is another course. Operation and control is another course. Power system optimization, market. So there are
Yes, sir.
several topics in power system. It's a even
Yes, sir.
distribution system itself is another topic. There is
Yes,
an
sir.
entire book on it. It's a very famous book. You can find NPTEL course in power system distribution system and analysis.
Yes, sir.
In that, I was telling that K factor method is there. That is also an approximate method and it is used. Okay. So in this week we discussed up to this point.
Yes,
Yes,
sir. Sure.
that application of capacitance was also there, but because in next week we'll be having questions regarding that, we will discuss that in the next week. Now
Sure, sir.
we will start with the questions. Otherwise, last time we were not able to solve all the questions. Without distributed approach. Huh? So shall we start questions?
Yes, sir.
Okay. So this first.
Sir, sorry, sir, but I want to ask, sir, is there any class you are sitting there?
No, I'm sitting in the lab.
Lab or library?
No, no, lab. It's lab.
Okay, so sir, like you go to the college and from there you are taking this live session.
Yes, in the college.
Okay, thank you, sir.
Okay, so this is the first question. This is objective question. Then next, all the questions will be these numericals. So we have discussed this point. So what will happen if the load in the distribution network increases? What will happen to the losses and stability? What will happen if
The
load increases?
losses increases,
Yes, loss will increase. And what about stability? Will it improve or it will worsen?
decrease,
Yes, so the
poor.
voltage profile will become it becomes poor because if we consider the radial system, so here it's at the far end of the distribution system. If the load here increases, then losses will increase and this voltage here, let's say we end, this will reduce. More the load increases, this voltage will reduce. So this can lead to this. So that's this voltage profile will be affected. So voltage will be here at substation, it will be maximum, and as we move along the feeder, the voltage reduces, it drops, and the increasing the load further reduces that voltage. But this is as per the conventional radial distribution system. But now things can change. Can voltage increase at this point even more than substation? Is it possible?
I think that it is possible when leading power factor load is connected.
Yes, that is possible. But generally, what happens? Most of the loads are our lagging loads.
Yes, sir.
So we use capacitor banks to means industrial consumers generally use, or big residential homes might be using it. But normal household consumers, they have lagging load and they don't use capacitance. So the voltage is less than the substation voltage. So any other reason why voltage can increase, voltage might increase at any particular bus.
Sir, due to lightning.
Well, lightning generally it happens in transmission lines.
Yes, sir. Transmission. Yes, sir.
But we are talking
So, distribution system. Mm, in distribution system, how can it increase?
just what will happen if there is even distributed generation or PV. So that at a particular bus there is load also plus PV. And load at a particular in daytime, suppose let's say load is very less and PV generation is quite high. Because of high generation, excess generation, voltage at that bus can increase. And it happens. And in daytime when solar output is more and the load is less, then at that time voltage can increase here
Yes.
at the bus. So this profile will change. This can
Mm.
this profile it can be anything, but it can become something like this also.
Mm. But sir, when we install large amount of PV, then it can increase. Like
So it will depend upon the uh, rating of that PV and other loads also in the vicinity up to the
sir.
substation. So it depends on, but it can happen. If let's
Yes,
say
sir. It can increase.
several homes, all these buses have PV installed, and
Okay.
daytime there is excess generation, then this can happen. This can certainly happen
Mm.
because we are injecting power from at each bus, and
Uh-huh.
that net injection, there is net injection. That means
Yes, sir.
the generation from solar is more than the consumption of the load. So there is net injection instead of withdrawal. So therefore, voltage can increase.
Mm.
So exactly what will happen that we need to study.
Yes, sir. We
But
have to study that.
voltage, but certainly voltage will profile will be better than this one. So voltage at this point will not be uh, very less. It can be near to the substation voltage if there is PV installed and it is generating, it is feeding into the grid.
Yes, sir.
Okay, so this is correct. Now we'll start with numerical. So do you have keep your calculator with you? We'll solve it. Huh?
Yes, sir. I have.
Okay. So this is the first question. The first question, it is similar to what we did last time also. First two questions are similar to what we did last time also. DC ring uh, radial DC ring mains distributor. So this is a ring main system. There is a ring That is why you will see here the voltage will, right, in radial system what happens, the voltage keeps on reducing as we move along the feeder. So voltage at the far end will be least. But this will not happen in this case, in the radial, in this, sorry, ring system. We will see here by calculating the voltage, we will see voltage if we consider that this is substation, because here what is happening, even this point, these 2 points are closer. Let's say instead of ring we have radial system. This is A, B, let's say this is B, this is C, this is D, this is E. So voltage of E will be least. It will be less than other. This will be the sequence,
Yes, sir.
right? But in ring system, now E is also closer to the substation, B is also closer. So now E voltage of E point will not be least. So that is why ring is better than radial.
Okay.
And even if in the next question we will see if there is one more connection in between, then what? Then it is even more reliable. Suppose there is a fault on this feeder, so this will be removed, but load can still be supplied like this. E can still be supplied. All the loads can still be supplied. Fault on any feeder, this feeder, that feeder can be removed, but still the loads can be supplied. So this is the benefit of using ring main. That is why you will see in campuses, college campuses, universities, big colonies are there. They have such a ring system. They will have 2 3 meshes. They are normally open. Let's say this can be, let's say this is, it is like this. Huh? So this will be normally, eh, these two connection will be normally open. Generally it will be, this may not be open, this may be closed. Let's say, so this, if these two are open, let's say, okay, then it becomes a radial system. A is connected to B, C, D and E. These two are open. But whenever there is a fault, if there is a fault here, then it will be closed. So although there is a mesh connection, but operation is radial only. They will only come whenever there is some fault or some maintenance is going on. So inherently it is a radial system. All the meshes are there. Operationally radial. Okay. Let me add one page. So have to copy. Okay. So let us say, this current is X. So how much will be this?
40 minus x.
X
No,
minus.
x minus 40.
Yes, and this will be X minus 50. This will be X minus 50. And this will be X minus. So we can write KVL here in this loop. And it is given that, so these are the section length, and the resistance is zero point 0.2 ohm per meter. So it will be zero point 0.2 into 2 for AB, 0.2 into 3, 0.2 into 3, 0.2 into 4, and 0.2 into 2. Let me write it here. 2. This is 200, 300, 300, 400, and 200. Okay, so now we'll write KVL. This will be x into 2 into 0.2 plus x minus 40 into 3 into point 2. 3 into point 2 plus x minus 80 into point 4. Sorry, 4 into point 2 and x minus 100. 2 into point 2. This is 0. So point 2 is it's common. So now can you tell what is this equation? Calculate.
Sir, x equal to 57.5.
There is some mistake. So what is your equation? This one in terms of x. This is 2 plus 3 5 plus 3 8 plus 4 12 plus 14x is equals to how much? 120 270 470 plus 3 790. Are you getting this?
Yes, sir, I am getting this. 56.42 x equal to.
Yes, correct. So now calculate ABV voltages. How much will be VA?
VA 200, no, 280.
No, sorry, VB. VA is 280. VB.
VB equal to 280 minus 56.42 into point 4.
Yes, how much is it?
57.432.
So this VC will be 0.43 minus x minus 40. So 16.43 to 3 into point. How much is this?
3.58.
How much?
223.58.
This one?
Yes, sir.
No, it's not correct.
Okay, okay, okay. 257.43, 16.43 into 3 into 0.2. That is 247.57.
Yes. Now next one. This will be much minus 50. So it is
Okay.
6.43 multiplied by 3 into point 2.
It's 243.71.
Hmm. Then last one is this minus. This will become negative.
Yes, sir.
56.43 minus. So voltage here will increase.
Opposite. No, it will opposite polarity.
Yes, it will be 4 into point 2. Correct. So how much is this?
That is 278.57.
No. 200. Check it.
78.
Check it once again.
No, sir. 278.57.
Oh, no.
No, no, actually,
Actually, I made a mistake. This is minus 80. This is 23.57. Because this we are calculating this one VE x minus 80. I did x minus 100. It is minus 23.57.
262.566.
So here you can see if if it had been radial, then this voltage would be least. But now among these four, VE is maximum.
Maximum, then like near to substation, it is
Yes,
maximum.
yes, that is why. Because here, if you see, this is 200 meter, this is also 200 meters. But at point B, load is drawing 40 amperes. Point E, load is drawing 20 amperes. That is why, because current drawn here is less. That is why voltage here is drop is less.
Drop is less.
Both are at same distance from the substation, but here drop is less. That's why voltage here is higher because of this ring connection. So VE will come V is highest, then followed by VP, then VC and VD. Okay, so this is the benefit of using a ring structure. Okay,
Yes, sir.
now this, yeah, so this is V's, yeah. So I was talking about this. Here we have one interconnector also. So this is more reliable. Here we need to find out the current in this interconnector CE. So how to do this? Here again we have to use the same concept. We'll write equations KVL. Okay, to copy this. Okay, so let us consider here. So let us say this current is I, this is X, this is Y, and this is some Z. So how much will be this current?
Sir, x minus 20 minus z.
Yes, x minus 20 minus z. And this will be x minus,
Z minus 50.
and toward this one, let's say this. How much will be this one? So
Y
y
minus 40.
is y minus 40. So now we can write two loops. We have two loops. KVL in two equation. First of all, we can. How much is I? Can you tell how much is I?
I is 50, 60 on 100.
Yes, I is 100. So total current here is 100 amperes. I. Then we have one more equation for I. I is also equals to,
X plus Y.
yeah. So if we write KCL at node B, then 100 is equals to x plus y. So we have this one equation. Now we can write KVL in loop 1. Let's say this is loop 1, and this we call as loop 2. So let us write KVL in loop 1. So how much is this? This is x into, so all these resistances are zero point 0.2 ohm per 100 meter. So this will be, this is 100, so it will be zero point 0.2 only. This is zero point 0.2 x plus, then this z. This is how much? Point 2.5 into zero point 0.2 into z,
5.
right? And this is equals to
0.5.
y minus, yes, it will be zero point 0.5. So y minus 40 into 1.5 into zero point 0.2 plus y into 1.5 into zero point 0.2.
Yeah.
So zero point 0.2 we can remove.
Yes, sir. We can do.
This will be x1 x plus, here or here this will be 2.5 z, and this is equals to how much y? 3y minus how much? 60. Correct?
Yes, sir.
Now write KVL in loop 2. So this will be x minus z minus 20 multiplied by zero point 0.2 into 2, then plus x minus z minus 50 into zero point 0.2 multiplied by 2. This is equals to z into 2.5 into zero point 0.2. So zero point 0.2 we can. So how much is this? 4z, 4x, then 4z minus 6.5z is equals to 40 plus, how much is this? Okay.
Okay, sir.
Now we need to solve these three. You can directly solve them in calculator, or what you can do, substitute remove y from equation 2. You can write 2 point,
Sir,
yes.
we can directly solve by the calculator.
Yes, so tell me what is the answer?
Yes, sir.
Calculate.
Three, zero. Sir, x equal to 53.05,
X is equals to, yes, correct.
y equal to 46.94,
Yes. And Z,
z equal to 11.11.
correct. Good. So this is correct. The same thing I've done here. So answer is 11.11. So this B answer is correct. So now this is another question. This is also simple. There are two distribution system. System 1, system 2. We have been given the sending and receiving end nodes, and it is given that all the lines have same impedances and load at all the buses are same. Load are also same for both the system, and bus one of both have 1.0 per unit. So which system has a better voltage profile? This we need to calculate. So let us draw first system 1. Everything is same, only difference is the network configuration. So what is system 1 is, it is starting at bus 1, then connected to 1 to 2, 2, 3, 4. So it is a radial. 2, then 3 is connected to 4. So it is completely radial. There is only one feeder, and we have load at each bus. This is system 1. Now what about system 2? It is starting at 1 to 2, 2 to 3, 2 to 3, then 3 to 4, 4 to 5, 5 to 6, 3 to 7, 7, then 7 to 8, 4 to 9, and 9 to 10. So these are the two systems. Everything is same, only this configuration is different. So what do you think? Which of these system will have a better voltage profile?
System 2.
Yes, correct. But why?
Because there is lateral branches, so at the node 6 the current is less than system 1 at node 9, because from node 3 to 6 only current carry by the bus is less than system 1.
Correct. So the voltage drop up to this point, this node 6 here will be less compared to.
Less this node 9.
So voltage drop at this bus 10 will be less as compared to this system here. Yes, 6 can have more voltage drop, but this will be certainly lower.
Yes, sir. I think they 6 and 10 will be same because two nodes are there, 5 and 6 and 9
Same
and 10.
impedance and every, yes, correct. Even this, all these will be same.
No, sir, but 8 will not same. Why? Because four,
Yes,
5, 6,
correct.
9, 10.
So yes, so 6 and 10 will be same because both are 7, just parallel.
Yes, sir. Yes, sir. Both have same node.
Yes, similar nodes. So you can say 6 and 10 are similar nodes. So they will have same voltages, correct, and better than this one. So system two will
Yes.
have better voltage profile. So this next question is also similar. You have to compare two distribution system and you have to tell which one is having better voltage profile. So here it is saying which system has better voltage stability index. So that we need to calculate. So here the loads are connected at receiving end uh, and bus of each line. And bus 1 is at 1 per unit. Which system has better voltage stability? Here if we see 1, 2, 2, 3, so it's a radial system. Both the system configuration is same. In the previous question, configuration was different, load was same. Here, configuration is same, load is different. So now, can you tell which one will have a better voltage stability index? So how will you calculate this? How will you determine, compare the two systems?
Sir, firstly, we will draw the diagram.
The diagram is same here because one, two, both the systems are same.
Same. Okay. So we will see the power
Yes.
drawing by
Yes.
the source load.
Yes. So how much is total active and reactive power here? Some calculate total. What is total?
5, 5, 9, 10, 16, 19, 1, 5, 7, 8, 9, 10. 1095.
And reactive power?
1720.
This one?
Yes, sir.
No, no. How? Once, 1720. QL, it will be less than PL. 9.
90, 910.
Yes. And this
This
one?
one. 1130. This one. PL KW.
Yes.
This one 1130.
So now here total demand is, total load is this much in system 1, and system 2 it is 1130 plus J925. So which system will have a better stability index? Network is same.
So system 1
Why?
is the total power is drawn by this system is less than system 2.
Hmm. Yeah.
That's why the current drawn by that system is less than system 2.
Hmm.
That's why the voltage drop in system 1 is less than system 2.
Yes, correct. So if the load increases, then there is voltage will further reduce here, much more than system 2. So yes, system 2 system 1 in comparison to system 2 has a better stability index. Good. So now let us move to the next last four questions. These are big questions. We will solve them. Now here we have to use method 2. So it is given that it's a radial network. So there are one, two, two, three, four. So it is like this. One is connected to two, is connected to two, three is connected to four. Simple three, four bus system. R and X value are given, P and Q are given. First of all, base voltage here 11 kV, MVA is 1 MVA. We need to find the voltage magnitude of bus number 4 after first iteration. So this V4 we need to find out, V4 1, first iteration. First of all, we need to convert these values into per unit.
Okay.
So what is Z base here? So KB base is known. KB,
121.
yes, correct. So 11 kV and MVA base is 1 MVA. So Z base is kV square by MVA base rate is 121. So calculate Z1, Z2, Z3. How much are you getting? So this PLQL we can directly write PL plus JQL. First one is 0.32 plus J 0.25 because we just divide it by 1000 because it is in kVA and base is MVA. This is 0.21 plus J 0.16 and this is 0.13 plus J 0.08. So calculate Z1, Z2, Z3. So I will add one page. Z2. How much is Z1?
Sir, Z1 is 0.02 plus J 0.009.
Correct. And Z2?
Sir, Z2 actual value I did not recall.
Z2 is this.
Okay.
And Z3 is 0.0308 plus 3.0178 per unit. So here we have to use method 2. In method 2 we need to make, uh, so we will start with initial initial guess that
Or 0.
losses are 0. So P0 branch 1 is equals to P loss branch 2 is equals to P loss branch 3. All initially are 0. So we have to do only one iteration here. And so now we need to find this equivalent PL and QL for each of these. branches. So what will be equivalent? So here, what will be equivalent P2? Here,
P2, sir, it should be
P2 plus J.
add P2 plus 0.21 plus 0.13,
Yes, and because loss is zero, so loss will be zero. So how much?
0.66.
0.66 plus Q2. Q2 will be sum of all. 0.25, 0.16 and point 0.08. So how much is this?
It is 0.49.
Yes, 0.49. So now we have P2 and JQ2. So we can find A and D. So
A and D as well.
we need to find A1 and D1. So A1 formula is this P2 R1 plus Q2 X1 minus zero point 0.5 P1 square. So how much is this? Calculate. P2 we know P2 Q2. R1 and X1 is also known. V1 is V1 is 1.0. Then V1 is A1 square minus R1 square plus X1 square into P2 square plus Q2 square.
Sir, A1 is come out to be minus 0.486.
Minus 0.48.
6.
486 or here. I'm
Yes, sir.
doing 2. Here, 0.48. 2. So, and how much is D1? Calculate D1. If A1 square, A1 is known. Now we can calculate D1 also.
Zero point 231.
And there is one square root also here.
0.481.
Hmm. 0.4818 something you will get. So now we can calculate V1. Sorry, V2 is D2 minus A1 again square root. So how much is this? D2 minus sorry D1 minus A1 square root of D1 minus A1. So you can check whenever you calculate A1 D1. A1 will always be
0.981. A1 always be negative.
yes
A
negative
will be.
always. A1 will be always minus D1. It's very close,
Okay.
especially for the first iteration. And
Okay.
for other iteration also, A1 will be negative and D1 will be positive, and the difference between them will be very less. Okay, so similarly, you can calculate this.
Yes, sir.
Next voltage P3. So what is P3 plus JQ3? P3 plus
Point
JQ3.
three four. Point 34.
0.34. Yes. 34 plus J point.
Point 24.
Yes. So here now again A2 we can calculate A2 as P3R2 plus Q3 X2 minus 0.5 V2 square, and D1 is A2 square minus R2 square plus X2 square P3 square plus PQ3 square. Yes. So how much
Sir,
is
in next station we will also include losses.
where? Yes, but this is iteration one only.
Yes, sir.
It, we will do that in next iteration. But here we are only asked to calculate voltage after first iteration.
And then, sir, next iteration we have to also calculate
Yeah.
current, branch current.
Why? We just need to, here we don't need branch current, we just need to calculate the
No,
losses.
no, sir. Next iteration. In next iteration.
The next iteration also, why to, because we just need to calculate loss, huh? No need to calculate current.
Then,
You
sir,
can
loss.
directly calculate loss. For calculating loss, you want to calculate current.
Yes, sir.
And that you can do. Directly also we can write.
Directly how, sir? Voltage square divided by resistance.
Yes, same. It is same. It's either you calculate current or we write it using the same expression.
Okay.
Because finally, losses have I square R. I square R. So it will be R into P square plus Q square by V square.
Then, sir,
And
reactive loss also we have to calculate. Reactive
so it
loss.
will be X into P square plus Q square by V square. So yes.
Okay.
So we no need to calculate current, just directly use this. So directly we
Okay.
can use this. So because
Then,
we know,
sir, I want to write this. I want to write I square.
okay, so I square R, this is R into P square, because I we know I is
Sir, this is magnitude.
P minus JQ P con. This is I, correct?
Yes, sir.
The magnitude of I will be this.
Under root P plus Q.
Okay.
Square plus Q square.
But now we need to calculate I square. The square will be A square
P.
and multiply it by R. So you will get R. Okay.
Yes, sir.
So directly use this. Uh, so now calculate A2 and D2. After that, we need to calculate A3 and D3 also. How much is A2?
Sorry, two I did not calculate. But sir, you can write. I will verify this.
Okay. It is minus 0.4696. This is 0.4694. So V2 you can calculate. V2 is D2 minus A2 So not V2, V3. So how much is V3?
It is 0.9688.
0.968. Okay, V3 आ गया. Now we can calculate V. So P P3 P4 plus JQ4 is same this one. Same. Then you have to calculate A3 and D3. So A3 will be minus 0.4640 and D3 is 0.4639. So V4 will be D3 minus A3. What is this? How much? V4?
That is 0.9632
So this is a voltage after
at
the
bus 4.
first iteration at bus 4. Now we need to calculate the voltage stability index. Next question. It is continuation of this only. Same question, but for same question we need to calculate the voltage stability index at bus 3.
Okay.
So we saw that formula for that. I will just write it here. This one, voltage stability is B square minus 4C. And after substituting this B and C value, we will get B square minus 4. So it will be V3 minus 4 V3 R. It will be 4 V3 X2 plus Q3 R2 square minus 4 V3 R2. So this is SI for bus number 4. Sorry, for bus number 3, not 4. So for this is for bus 3. For bus 4, this will change. These values will change. It will become P4X3 Q4X R2 R3. So for bus 4, it will be mm,
And the voltage will not change V2.
yes, yes, voltage will change. This will become V3 for
Okay.
bus 4.
S4.
P4 R3 plus Q4 X3 into V3 square. Yes, so you can calculate this. So this will come out to be 0.8816. This I have not calculated. So answer for this is 0.88. 0.8, yes. This is point rated answers. The answer is correct. Okay, so this is the last question. These are also two questions. So we saw this derivation for approximate voltage drop, right?
Yes, sir.
So here, what is shown? Assume that power factors of load current are given with respect to voltage at bus 1. Calculate the approximate voltage drop across the feeder from point 1 to 4. So we need to find out voltage drop from 1 to 4 using approximate method of analysis. The next one is using exact method. Okay, let me add the page is already there. So first of all, let's calculate this current. All these are lag. So how much is this current I2? I2 is 30 angle cos inverse. So this is cos phi, 0.85. Sine will be so is we are writing cos theta and sin theta because formula is formula for voltage drop is which I r cos theta plus x sin theta. So Rx is this. I is this branch current. So we need to find out I1, I2, I3 also. This one is how much is sin theta here? Okay. So first of all calculate this I1 branch current. How much is branch current?
100. 100.
How?
Sir, 30 plus 20 plus 50.
We cannot directly write like that because it is at an angle. Huh? I1 is I2 is this 30 angle minus 31.7.
Okay, it is in phasor.
Yes, it's a phasor.
So first we have to convert it in rectangular form.
So there is another method. Same. If we write, suppose. So what will be voltage drop? If I write,
Here,
let's say, if I write
I,
voltage drop VD12 will be in the
I1
in terms of these currents, it will be I1 plus I2 plus I3 into
into Z.
R plus JX. ठीक है? R1
Okay.
and VD. Suppose I want to write overall total. So then next term will be how much? I2 plus I3 into
Into
R2 plus
R2 plus
JX,
JX2.
and last
Yes,
one
sir.
will be I3
I3.
R3 plus JX3.
Hmm.
Oh, sorry. I think this is I2, I3, I4. This is I3 and I4, and this is I4. Okay.
Yes, sir.
So now if we club these terms, if we take I2 common,
We will get
so then it
voltage.
will be only R1 plus JX1, no? Correct?
Yes, sir.
And then for I2 it will be, sorry, I3. I3 it will be R1 plus R2 plus J X1 plus X2.
No, sir. But how?
Here take I3 common. I3 is coming here. I3 is coming here. With the R1, I3 is being multiplied only by these two terms. Eh?
Yes, sir.
That's why. Clear? Then I4 is coming in all the three terms. So it will be R1 plus R2 plus R3. Okay?
Hmm.
Correct?
Yes, sir. And I2 is coming only this term.
So I2
I4
is
is
having only this R1 plus X1. I3
yes, sir. Yes, sir.
R1 plus R2. And last
Yeah, yeah.
is all the three. So it's just rearranging the terms. So what we can write? So VD1 we can write as I1, sorry, not I1, where is that? So it is not a capital I1, it is small I1. So small I1 into R1 cos theta plus X1 sin theta. So how much is this? 30 into R1 is X1 is 0.01. How much is this? Calculate. So VD2 will be I2. This is not, this is I2. This is I3. That is R1 plus R2. This is 0.05 plus 0.08 into point. 3 here is 20. Is this method clear?
Yes, sir.
So this will come out to be 1.433 and this is 2.8631. Similarly for VD3 So
Sir, here you did not consider the angle of current.
no, we are considering it because what we are writing here is it is I4 into R1 plus R2 plus R3 into cos theta. This theta is because of this current only. So what we are doing, we are writing I4 as I4 magnitude.
Cos theta plus j sin theta.
Yes. Then you multiply it with R and X
R and X.
because this we are considering only the active voltage of, not reactive part, that we are neglecting for approximate method.
Okay. Okay.
There will be no
Means we are
term,
not considering here
imaginary
X.
part. No, we are considering because this I4 is cos theta plus j sin theta, and then we are multiplying it with z. Z is, let's say, r
R.
dash plus j x dash. So now we are multiplying
Okay.
these two terms. So there will be one real term and one imaginary term. So we are neglecting that imaginary term. But in real term also r and x both will be multiplied. So
Hmm.
it will be I4 cos theta into r dash plus I4 sin theta into x dash.
Yes, sir. J square minus 1.
Yes.
It should be minus sin term.
You're saying this one?
Yes, sir.
Cos theta. No, actually this is negative only. Because sin theta is negative, no? Lagging. It's a lagging current.
Okay, okay. It's a
That's why
lagging current. Okay.
theta is negative, no?
Hmm.
The currents are lagging, so that is why it is cos theta minus j sin theta. So it becomes positive. Okay.
Sir. Correct. Yes, sir.
So we are neglecting. Then there will be two other terms also. That with they will be imaginary. So we are neglecting this part. So we will be having only this component. So VD3 will be this cos theta plus x1 plus x2 plus x3 into sin theta. This is zero point 0.8. This is zero point 0.6. This is 50. And substitute R1 plus R2 plus R3. This will be 11.6 volts. So total voltage drop will be summation of VDI. I is equals to 1 to 3. And this is 16 volts. Approximately 16 volts. Okay. So this was using the approximate method. Okay. So now this is the next one. Here we need to find out the per phase kVA output of the distribution transformer using the exact method. So I1, I2, I3 we have calculated. So here we need to calculate the exact method here. We will use the exact equation. So V2 is equals to V1 minus I1 branch current into Z1. So V3 will be V2 minus I2 into Z2, and V4 will be I3 into Z3. So first we need to calculate I1, I2 and I3. Okay, then we need to calculate the kV output of transformer. So how will you calculate kVA output of transformer? So how much?
KPA output.
Yes. So we know this current.
11 kV. No.
We know all these currents, I1, I2, I3, because we know these currents. So I1 will be summation of I2 plus I3 plus I4. I2 will be and I3 will be I4. So we know this. We know V1 also. V1, assume that power factor of load. So V1 will take us V1 is already given 220 volts. So V1 is 220 angle 0. So we know V1 and I1. So can you calculate kVA output of transformer? How? What will be? How much is S?
Sir, in per unit we have to calculate.
No, average. Here all these values are in ohms. Huh? Current, no, nothing.
Okay.
Current is also no. Everything is in base. All these respective values. These are not per unit values.
Sir, this value we can note it directly because it is in phasor, right?
No, we can calculate na S. How much transformer? How much power transformer is injecting, supplying? How much power is on the secondary
22
transformer?
kV. No, 22 kVA.
How?
Secondary system voltage.
Because
Sir, voltage is 220 and current is 100.
where is current? We don't know. It is not 100 na, because we have to. These are phasors. Add them as phasors. So it will be V into I1. We need to calculate first. Add all these three currents. So actually it will be close to 22 kV only, because these are phasors. So magnitude will be close to 100 ampere. But exact value is not 100. So first of all calculate I1. Let's calculate I1. So do it. At least just calculate these two values. So this is I2, small I2. Small I3 is 20 angle 84, and small I4 is 50 angle minus 36. So calculate I1. I1 is sum of these three phasors. How much is I1? How much?
Sir, I am getting 99.72 Angle minus 33.14.
Yes. So this is I1. Now we know voltage is known. We can calculate power. This is 22 angle 0. Calculate how much. So that you can see this is close to 100 ampere. So calculate this one. S. How much is this? So multiply your and take a conjugate and multiply it with voltage.
So it is coming 21,938,938.39 angle 33.14.
Correct. So this is per phase. So for three phase, you multiply it by three. So this will
They
be
are
the
asking about this
thing. This is only they're asking only per phase.
per phase.
We need only this value. This will be the per phase kV output of transformer.
Yes, sir.
So here we are not using any kind of approximation.
Yes, sir.
So here in this previous case, here we were using approximation.
Like here we are discarding the imaginary term,
Hmm.
but here we did not did.
Also, we are considering here that cos the delta is very small.
Mhm.
So we are not considering the cos delta here. Here is that we have derived that. This one. So cos delta, this also we are not considering in approximate method. Okay.
Yes, sir.
Okay. So all the questions are done. We'll see next time. We will see capacitance and I think application of capacitance in distribution system. Okay.
Okay.
So try
Thank
to
you,
start.
sir.
Thank you, Deepak, for joining.
Thank you so
You
much,
can
sir.
ask if
Bye,
you have
sir.
if you have any question, you can ask in next time.
Yes, sir.
Okay.
Sure,
Bye.
sir.